SPH4U, wave nature of light. 5.1 properties of waves. So here we're just going to go over the properties of waves that are both applicable to light waves and other types of waves. So transmission of waves. So a wave that originates from a point source is circular. So let's just say that you have a still pond and you have a droplet going into here. So this is where the droplet hits, and then the waves radiate out from it. So a wave originating from a linear source is upright. So if all the waves are coming from something like this, like a linear source here, then all of the waves, they will be upright. So for example, these would be the class of what a wave originating from a linear source would look like. So transverse waves are periodic disturbances where particles oscillate in the medium at right angles to the direction at which the wave is traveling. So this is an example of what a wave would look like. So it follows the same shape as a sine or a cos function. So the amplitude is the distance from the equilibrium to either the class or throw. They are equal because equilibrium is the axis of this function, or basically the midpoint between the class and the throw. So the class is the maximum and throw is the minimum. Wavelength is the distance between two class or two throws, and that's typically in meters, and is signified by the Greek letter lambda. And the frequency is 1 over t, and it's measured in hertz. So with these two concepts, we can actually get an equation for the speed of a wave. So recall that the velocity is equal to distance over time. So if we make it velocity is equal to wavelength over time, wavelength is in the same unit as displacement, we get the equation v is equal to f times lambda. So the velocity of a wave is equal to its frequency times its wavelength. So now we're going to talk about reflection and refraction. Just one important note is that the speed of light, which is a constant that will be quite important in this course onwards, is as follows. Speed of light is equal to 3 times 10 to the power of 8 meters per second. So let's go on to the deflection. So deflection is when a wave, in this case a light wave, hits the surface and it bounces back. And the normal, it is a line perpendicular to the point of contact with the other surface. So the angle of incidence is the angle between the instant ray, so this is the instant ray, and the normal. And the angle of deflection is the angle between the deflected ray and the normal. So this is the deflected ray. So angle of incidence is described via theta I. The angle of deflection is described by theta lowercase r. So refraction is the bending of a wave's direction that occurs when the wave enters a different medium at an angle. So the angle of incidence, so same theta I, is the angle between the instant ray and the normal. So normal is perpendicular to the barrier between the two mediums, and yeah, so that's theta I. And then we have the diffracted angle. So angle of diffraction is described by theta big R, and it's the angle between the diffracted ray and the normal. So here in this diagram, it is described with theta big I, but yeah, you could use theta big I or theta big R. Alright, so Snell's law is n1 sine theta 1 is equal to n2 sine theta 2, where n is equal to the absolute index of refraction. So that will be a constant that will be given to you depending on what medium is being discussed. So the absolute index of refraction of substance 1 times the sine of the angle that the ray is going through in this medium is equal to the absolute index of refraction of the second medium and the sine of the angle at which that ray is now refracted. So there's some relations that we can make. So n2 over n1 is equal to sine theta 1 over sine theta 2. So make note that the subscript 1 at the bottom here is here on the top. So, and the subscript here at the top is here on the bottom. So that is also equal to v1 over v2, so the velocity of those rays, and that's equal to lambda 1 over lambda 2, so the wavelengths of those rays. So these are some very important and useful relations. So now we're going to talk about diffraction of water waves. So diffraction is the bending effect on a wave's direction as it passes through an opening / an obstacle, and shorter wavelengths are diffracted slightly while longer wavelengths are diffracted more. And another thing is that as the width of the opening by which the wave is going through becomes smaller, the diffraction becomes higher. So there's this relation that we can use, lambda over w. So w is the width of the opening, should be greater than 1. So that's the relation that you can use. And so I'll just draw these visually for you. So we have a wave with shorter wavelengths, and then it goes through this aperture. So then it gets diffracted like this. Well, you have this longer wave that's going through an aperture of the same size, but in this it gets diffracted much more. And then now on the width of the opening, so let's just assume that these wavelengths for both waves are the same, and so we have this wide opening, so this gets diffracted slightly. Well, we have the same wave going through a smaller opening, then it gets diffracted more. So yeah, that's a quick intro into the diffraction of waves and the properties of waves in general.